Welcome back to Lesson 7 of our General Emergence Mechanics Explainer. Today, we're really putting it all together. We spend a lot of time exploring these hidden quantum rules, but how do those rules actually step out of the vacuum to govern the reality we experience every single day? Well, today, we are going to deconstruct the exact physical levers the universe uses to build a stable system. We'll look at why those systems break down and, crucially, how we can use this knowledge to engineer better recovery for our own bodies.
Here is our roadmap for today. We are going to systematically build up an understanding of how systems survive, fail, and recover, moving from the basic anatomy of stable systems all the way to a universal language of resilience.
Okay, let's dive into this with part 1. The anatomy of stable systems. Essentially, the universe fights decay using 3 fundamental mechanical levers.
Level 1 is depth, which is represented by the letter D. Now think of depth like a giant energy basin. The deeper that basin is, the more environmental chaos the system can absorb before it's completely wiped out. Whether we're talking about a microscopic quantum particle or a massive steel bridge, absolutely everything that exists has to possess enough depth to avoid being erased by random, everyday noise.
Level 2 is stiffness, or kappa. If depth is your overall limit, stiffness is your immediate pushback. Imagine for a second the difference between trying to snap a dry, dead twig versus bending a live, green branch. The dry twig has incredibly high stiffness. It resists with rigid force right up until it breaks. Stiffness dictates exactly how hard a system pushes back the very instant it gets disturbed.
And finally, we have viscosity, defined by tau. This is all about your recovery time. Does a disturbed system snap back to its original shape instantly, or does it sort of ooze slowly back to normal like thick honey? A highly viscous system actually holds on to stress for a lot longer. It's almost like it has a physical memory of the event. Together, these 3 variables, depth, stiffness, and viscosity, they form the 3 undeniable axes of a stable existence.
Moving into part 2, how and why things break. What actually happens when these 3 physical levers get completely misaligned under stress?
And what's really interesting about this slide is how it perfectly maps out why things fail. Let's look at the top scenario. If you have high stiffness but low depth, it means your system is super rigid but can't really absorb any energy. So a sudden impact, boom, brittle collapse. It literally just snaps. Now look at the middle row. Low stiffness and high viscosity. This means the system gives way really easily and recovers super slowly, which leads to creeping distortion. It essentially gets stretched out of shape permanently. And the bottom row, high depth and high viscosity. The system survives chronic stress, sure, but that slow recovery traps it in a distorted, unnatural state. It's stuck. And this brings us to a really crucial mathematical threshold. For a system to actually exist, rather than just being a transient quantum blip, its persistence time under stress absolutely must outlast its recovery time. Put simply, to be a real stable thing in our universe, you have to be able to outlast your own recovery.
Okay, part 3, real-world persistence mechanics. Let's take these failure modes out of the abstract and apply them to the macroscopic world we actually live in. Just compare a fleeting, transient quantum excitation to a persistent, stable, biological organism. The really incredible insight of GEM here is that the exact same mechanics, allowing a quantum field to stabilize into a particle, well, those are the exact same mechanics that allow a human body to maintain long-lived health and coherence under pressure. We literally see these rules playing out everywhere. A massive metal beam facing cyclic stress relies on its depth and stiffness, but if it doesn't get recovery time, it suffers physical fatigue. Or think about a traffic jam. A highway bottleneck acts exactly like a system with low stiffness and high viscosity, causing those frustrating cascading delays. But most importantly, think about your own body. When you struggle to fight off an illness, your body falls into that trapped metastability we talked about. You totally have the depth to survive, but a high viscosity traps you in a state of chronic inflammation. Let's move to and see how this builds into part 4, the biological coherence pod. Because if human illness is basically a physical persistence failure, could we actively engineer a physical persistent solution?
As researcher Peter Baldwin beautifully put it, the body becomes not merely a biochemical machine, but a multi-scale persistent system whose ability to recover depends on resilience, adaptive response, and recovery time. Reframing biology in this purely mechanical way is a huge deal. It means we can design a controlled persistence environment to manually support the body.
So what does this sleeping suit or coherence pod actually look like?
Well, step 1 is the biological interface. This is a soft contact layer that gathers real-time sensing and thermal data. Step 2 is posture and support. By creating a really stable geometry, we artificially boost your structural stiffness and minimize mechanical stress. And step 3 is the chamber shell. This acts as a rigid boundary that controls acoustic and thermal noise, which essentially acts as a shield to protect your depth.
By aggressively quieting down all that environmental noise, the pod basically acts like a localized vacuum shell for your body. Using real-time, closed-loop sensors, the pod introduces these subtle, low-intensity thermal shifts or vibrations. It's actively guiding your highly viscous, stressed-out biological systems back down to a stable baseline. It literally prevents that persistence drift that leads to chronic fatigue.
Finally, part 5, the universal language of resilience. Let's pull the camera back and synthesize what all of this really means for us.
So the crucial point is this: depth, stiffness, and viscosity form a unified, completely mechanistic language for reality itself. Whether you are looking at the fundamental constants of the universe, a fatigued steel beam, or the chronic stress trapped inside a human body, it is all governed by the exact same physical levers. And understanding them, that gives us a practical, real-world toolkit to design ultimate resilience in our systems and our lives.
I want to end this explainer by leaving you with a thought. Take a look at your own habits, your projects, the biological and daily systems you rely on. Ask yourself, what structures in your life are merely transient excitations, bound to decay under stress? And what truly possesses the depth, the stiffness, and the recovery time to persist? Thank you so much for joining us for this explainer. Keep questioning the mechanics of reality, and we'll see you next time.